Okay, we've got a question here. Very kindly tells us this is going to be an exact binomial test, but in an exam situation we would have to recognize what kind of test we want. Okay, it does at least say it's an exact test. That's a bit of a giveaway. That means it's going to be either binomial or Poisson. So what claim am I testing? The claim is that the proportion of students absent is 3%, okay? And I'm looking at 532 students and counting how many are absent. So I'm counting the number of absences in 532 trials, so that's why this is binomial, okay? So we know that x is going to have a binomial distribution with n is 532, but we don't know what p is. The claim is, okay, so in part A, our null hypothesis, H0 and H1, okay, we can say these in words or symbols. In fact, it's quite nice to say this in symbols. For setting up the hypotheses, I can say that my null hypothesis, well, the only exact figure I've got to work with is the 3%. So this is the headmaster's claim that P is 0.03. Okay, now, the alternative hypothesis, I need to look in detail at the claim. I am investigating the head teacher's claim, and the head teacher is claiming that the average proportion of students is 3%. Okay, so he's not claiming that it's more than 3% or less than 3%, he's claiming it is 3%, so any evidence that P is not equal to 0.03 will be against the head teacher's claim. So, I've got my hypothesis set up. Remember the 5 stages for a hypothesis test. Hypotheses, test statistic, critical value, comparison, conclusion, and context. So the next thing is to work out my test statistic. So my test statistic, okay, is just the probability. So what probability are we interested in? Well, the observed value is that 12 were absent on that day. So my test statistic is going to be the probability that x, okay, is something in relation to that 12. Okay, it's always an inclusive probability we work out, but what we need to think about is which tail of the distribution I might possibly be in. So I don't at the moment know whether 12 is higher than the head teacher would claim or lower than the head teacher would claim. And in fact, I've got to work that out. I've got to find out, according to the head teacher's claim, how many students would be absent. Well, there are 532 pupils. The head teacher claims 3% would be absent, so I need to work out 3%, so that's 0.03 of the 532. So if it was exactly 3%, then that would be around about 16 students, okay? But in reality, 12 are absent on that day. So it's a small figure. So if this is going to be evidence of anything, it's got to be because 12 is small, so we have to look at the small end of the distribution. That's the probability that's going to be less than a half, if anything is. Okay, so the probability of x being less than or equal to 12 is the one that I've got to find. So I've got, I'm doing exact binomial. I've got a probability of being less than or equal to 12, so I'm going to do my box diagram, though it's a very simple one. 13, ... So this is the probability of all of these put together that I expect to be less than a half. Okay, so I would need to work out the probability being less than or equal to 12. It's just a straight binomial from my calculator. So I do menu 7, binomial CD 1. Okay, put in my values. So x is 12, because I'm doing the probability being less than or equal to 12. N is the 532. The P is 0.03. Press equals, and we get our probability is 0.1918. So my P equals 0.1918, and that's my test statistic. So that's the probability, okay, that if the head teacher is telling the truth, that I would get 12 or fewer students being absent. Okay, critical value. Now the critical value, okay, for these tests, because I'm already working with a probability, all right, the critical value comes pretty directly from this. What you've got to decide, though, is whether to double it or not. So, as always, draw a diagram, but we're just working with probabilities, all right? The critical value, the critical region, has to have size 5%. But it's a two-tailed test, okay? This is not a one-sided alternate hypothesis, so therefore I'm interested in this and this tail. So this is 0.025. This is 2.5% of probability at each end of the distribution. So my critical value, in this case, it isn't just this as a probability, it's this case where we have to halve it. So on a two-tailed test, that's why we have to halve the significance level to get our critical value. So our critical value is 0.025. So to be evidence of something, I'd have to be in one of these tails. I'd have to be in a tail region with a probability of 0.025. Is this probability in that tail region? Well, no, 0.1918 is here. So I am in this big not significant bit. So my comparison is to say that my 0.1918 is bigger than my 0.025, and so we write not significant. Okay, that's fine for my comparison. I now need to do a conclusion. In context, well, we know that whenever it's not significant, that means we do not have evidence. So I start by saying no evidence at the 5% level, that, okay? And now I need a verdict on the head teacher's claim. So I'm going to be concluding about the head teacher's claim. So am I going with the head teacher or against the head teacher? Well, the null hypothesis is that P is 0.03. If it's not significant, that means we always accept H0. So if I'm accepting H0, then I'm accepting the head teacher's claim. So I must be saying that there's no evidence that the head teacher's claim is not true. Okay, so the head teacher claimed it was 0.03. The outcome of 12 students being late wasn't all that unlikely according to the head teacher's claim. So therefore, it wasn't in the critical region on either end of the distribution. So the head teacher's claim has survived our test. Okay, we didn't get evidence that it wasn't true. So that completes the essential hypothesis test. The question finishes in part B. So I've done part A. Part B says, explain a necessary assumption about student absences that's required for the test to be valid. So, student absences. What's my test based on? Well, at the very beginning I set up a binomial distribution. That was appropriate because I'm counting the number of absent students out of 532 trials. And I'm testing that this 3% probability, that's a claimed fixed probability. So it's not P being fixed, I'm assuming, because that's the claim I'm testing. But the other feature of a binomial we need is the trials need to be independent. Okay. Now, is that necessarily true? No, because if students are absent, if they're absent because they're ill, then they could be infecting each other with their disease. If they're skiving off, then they could be skiving off in groups of students. So whatever reason they may have, it may not be independent. Anyhow, we're assuming it is because we used a binomial distribution. So we have to assume. Absences are independent events. May or may not be true, probably isn't true, but that was the basic assumption. It's probably near enough to be true that the test isn't totally rubbish.